Hello everyone. In the last video we learnt about the definition of analytic functions. Today we are going to continue with the same topic. So this theorem says that if derivative of function is 0 everywhere in a domain D, then function must be constant throughout the domain D. Okay. So if you have any function fz whose derivative is 0 everywhere in the domain, then the function must be a constant function throughout the domain. So we'll prove this theorem. So let function fz be equal to u plus iv, where u and v are both functions of x and y. Okay. So since derivative exists and we know how to calculate derivative is u derivative x plus I v derivative x. So if derivative is 0 everywhere, then because derivative is given by u derivative x plus I v derivative x, so this must be equal to 0. And since the real part plus imaginary part is 0, so each of them must be equal to 0. So u derivative x is 0 as well as v derivative x is 0. Also because the Cauchy-Riemann equations hold, because the derivative exists. So by Cauchy-Riemann equation ux is vy and vx is minus of u derivative y. So by Cauchy-Riemann equation the derivative f dash j can also be written as v derivative y minus I u derivative y, and because derivative is 0 this must be 0, and so the real part v derivative y must be 0 and the imaginary part u derivative y must be 0 throughout the domain. So this immediately implies that the derivative u with x must be 0, u derivative y is 0, v derivative x is 0 and v derivative y is 0 at each point in the domain D. Okay. So now what we have to prove is that fz is u plus iv. So we just want to prove that u is a constant function and v is a constant function. If they are constant function, then fz automatically becomes a constant function. So our next step is to show that u is constant along any line segment L that extends from point P to some another point P dash and lying entirely in domain D. So say you have a domain D and say P is any point and P dash is any other point in the domain, and we can connect these 2 points P and P dash by a straight line L. Okay. So let S be the distance of point P from P dash and capital U be the unit vector in the direction of increasing distance. So by calculus result we can calculate the directional derivative of function u along this line. So du by ds is gradient of u dot product with the unit vector, which is capital U. Okay, where gradient u we know that it is partial derivative u with x I plus partial derivative u with y j, and since at each point on this is inside the domain, and at each point the partial derivative u with x is 0 and u with y is 0, so definitely the gradient of u is 0, and if gradient of u is 0, so du by ds is also 0 along this line. Okay, so this immediately gives us that du by ds is 0 along the line L, and since the derivative is 0 along the line, so this means that u must be constant along this line. Okay, so u must be a constant function on this line. Okay, so say now we have 2 points P and Q be any points on the domain, and we can easily see that any 2 points on the domain can be connected by a finite number of straight lines connected end to end. So we can join P and Q keeping straight lines entirely within the domain by going from P to P dash and going P dash to Q. Okay, so if you have any 2 points, they can be connected by finite number of straight lines joining end to end. So and since this is possible, then it means that u must be constant everywhere on the whole domain. Okay, so if this is true, then u, we can say u is a constant function, u equals a throughout domain where a is a constant number. Okay, the same procedure can be done with the function v, and we can prove similarly that v is also a constant function throughout the domain D. Okay, and because fz is u plus iv and u and v are a and b, so we can write fz as a plus bi, that is a fz is a constant function at each point in the domain D. So this is one result that you should remember, that if the derivative of function is 0 throughout the domain, then function must be a constant function throughout that domain. Okay. One important result, okay, from which we can prove using that theorem is, suppose that there is a function fz which is u plus iv, and this function is analytic in the domain, and also its conjugate which is fz bar which is u minus iv is also analytic. So that means the function and its conjugate are both analytic in the domain D, then function must be a constant function throughout the domain. So we'll prove this result now. Since function is analytic, so the Cauchy-Riemann equations will hold. So we can write that u derivative x equals v derivative y, and u derivative y equals minus of v derivative x. Also, because the conjugate function is also analytic, so the conjugate function will also satisfy the Cauchy-Riemann equations. Okay, so what exactly here we mean is that this first is the for the function fz. If fz is u plus iv, then the first result says that the real part x derivative, that is ux, is equal to imaginary part y derivative vy. Okay, and the second says that the real part y derivative is minus of imaginary part x derivative. So if we have this function f conjugate, then the Cauchy-Riemann equation will be x derivative of this must be equal to y derivative of the imaginary, and y derivative of real part must be minus of x derivative of the imaginary part. So we can write the Cauchy-Riemann equation as u derivative x is minus of v derivative y. Okay, that's the first Cauchy-Riemann equation for conjugate, and u derivative y must be positive v derivative x. Okay, so u derivative y is negative of imaginary, and it is already negative, so it becomes positive here. Okay, so the u and v function, they satisfy all these four equations. So from the first equation of these two, if we add these two, then immediately you can see that u derivative x must be 0. Okay, so if we add these two, then u derivative x will become 0. And similarly, if we subtract these two, then u derivative y will also become 0. So this immediately gives that u derivative x is 0 and v derivative x is 0 in the whole domain. Okay, so because function is analytic, then the derivative of function exists, and we know how to calculate derivative. F dash z will be u derivative x plus I v derivative x, and because ux and vx are 0, so that means derivative of function must be 0 throughout the domain. So because fz is analytic, the derivative which is calculated as this must be 0 throughout the whole domain. And so then by previous theorem it says that if derivative is 0 throughout the domain, then function must be a constant function. So it immediately gives us that fz is a constant function throughout the domain. One second result is that suppose that you have a analytic function fz, and fz is u plus iv, and further assume that the modulus of function, okay, is constant throughout the domain, then function must be constant throughout the domain. Okay, so if you have an analytic function whose modulus is constant throughout the domain, then function itself must be constant throughout the domain. So let us prove this result now. Since modulus is constant, so we can take modulus as equal to constant c, okay, for every z value in the domain where c is a real constant. Now if c is 0, if this constant is 0, then immediately the function will be 0. Okay, if c is 0, then this is only possible when function itself is 0. Okay, because modulus of function is u square plus v square under root, and if that is 0 then u square plus v square must be 0, which implies both u and v must be 0. Okay, and if u v are 0 then fz must be 0. So if c is 0, fz is 0, and fz 0 means function is a constant function everywhere. Okay, the second possibility is that c is non-zero. So if c is non-zero, then we can square this and write that modulus of fz square is equal to c square, and this left hand side can be written as fz into f of z bar, so that's conjugate of fz. Okay, so this is u plus iv, this is u minus iv, so that means it is u square plus v square, right? And because c is non-zero, then it immediately means that fz is never 0 in the domain. Okay, because if fz is 0 then conjugate is 0, so this non-zero equals 0, which is not possible. Now if function fz is never 0 in the domain, then we can divide with its fz to write that fz bar is c square by fz for all z in D, and because fz is analytic function, so c square by fz is also analytic, that means fz bar is also an analytic function. So what we have proved that if fz is analytic and modulus is constant, then fz bar is also analytic. So what we have is that the function and its conjugate are both analytic in the domain. So previous result, now it says that if it is true, then function must be a constant throughout the domain. Okay, so that's a very simple proof for this problem. This definition is about harmonic functions. If a real valued function h of two variables x and y is said to be harmonic in a given domain of the xy plane, if throughout the domain it has continuous partial derivatives of the first and second order and satisfies the partial differential equation, this and known as the Laplace equation. So this equation says the second derivative of h with x plus the second derivative of h with y must be 0. Okay, where h is a function of x and y. So any function h of two variables which has first and second order partial derivatives continuous and satisfies this equation, okay, the Laplace equation, then this function h is called harmonic function. Okay, so if you are given any function and if you have to check whether this function is harmonic or not, then its first and second derivative must be continuous and this equation must hold. Okay, so if you have, say for example, polynomials, then we know that polynomial equations are continuous and their partial derivatives exist. So we just need to check whether this Laplace equation is also satisfied by that polynomial equation or not. Okay, so we take say first one theorem which says that if a function fc which is u plus iv is analytic in a domain D, then its components u and v are harmonic in D. Okay, so it's a very important result which says that for if you are given any analytic function, then the real part must be harmonic and imaginary part must be harmonic. Okay, so if you are given any function and if we ask you whether this function is analytic or not, then you must check first that u and v must be harmonic. If u and v are not harmonic, then function cannot be analytic. Okay, so we'll just prove this theorem first. Say assume that the function is analytic in D and the partial derivatives of its component functions, partial derivatives of u and v exist and they satisfy the Cauchy-Riemann equation. So that means the ux is vy. Ux means partial derivative of u with x and vy means partial derivative of v with y. Okay, so that's first Cauchy-Riemann equation. And u derivative y equals minus of v derivative x. Okay, so a function is analytic, definitely it is differentiable and it satisfies the Cauchy-Riemann equation. Okay, again differentiating this is equations with respect to x. So if we differentiate the first equation with x, then it is the u derivative with x, okay, and v derivative with yx. Okay, So second derivative of u with x, and this second derivative of v with y and x. Similarly, differentiating this with x means u derivative y is already there, so a x derivative of this, so u derivative yx and minus of v derivative xx. Okay, so this is one equation. Similarly, again, if we differentiate the Cauchy-Riemann equation with respect to y, then differentiating the first equation with y means u derivative xy equals to v derivative yy, and u derivative yy equals minus of v derivative xy. Okay, so we obtain these two equations. Now, since the uh, partial derivatives, these mixed partial derivatives are continuous, so from this first equation and this fourth equation we can substitute vxy as minus of uyy here to see that uxx satisfies uxx is equal to minus of uyy, which immediately means that uxx plus uyy equals to 0. And similarly, the second and fourth equation, if I substitute uxy here, then because uxy and uyx are same, so vyy is minus of vxx, and so it gives that vxx plus vyy is 0. So second derivative of u with x plus second derivative of u with y is 0, so that means u is a harmonic function, and second derivative of v with x plus second derivative of v with y is 0, which means that v is harmonic function. Okay, so this is again an important result to remember, that if a function is given analytic, then its real part must be harmonic and its imaginary part must be harmonic. That means they satisfy this equation. Okay, one important point here, that if a function is analytic in a domain D, then we say that V is a harmonic conjugate of U. Okay, so what we say is that the imaginary part V is the harmonic conjugate of the real part U. Okay, so reverse we do not say, that means we do not say that U is a harmonic conjugate of V. We only say that V is a harmonic conjugate of U. Okay, so the imaginary function is a harmonic conjugate of the real part. Okay, so this is true whenever function is analytic, the imaginary part is a harmonic conjugate of U. Okay, so I'll just give you this statement and one examples, which says that if V is a harmonic conjugate of U in some domain, it is not in general true that U is a harmonic conjugate of V there. Okay, so what we mean, that if V is a harmonic conjugate of U means FC is U plus IV is analytic. Okay, and if we say U is a harmonic conjugate of V, that means we are saying some function which is V plus UI. Okay, so this statement is entirely different. Say just to explain this again, say suppose that U is this function x square minus y square, and V is a function 2xy. Okay, and first thing you can check that the U function is harmonic and V function is also harmonic. Okay, so second derivative of U with x, which is 2, and second derivative of U with y, which is minus 2, so their sum is 0, and second derivative of V with x is 0, second derivative of V is y is 0, so those sum is again 0. Okay, so they satisfy Laplace equation, they are polynomial type equations, so harmonic functions, both of them. Okay, now it is known that if I write fz is equal to u plus iv, that means this plus I times this, then this function is well known, it is z square function. Okay, so z square, if z is x plus iy whole square, then it is x square minus y square is the real part, and 2xy is the imaginary part. Okay, and we know that this polynomial function is an entire function, that it means it is analytic everywhere. Okay, so immediately we can say that v is a harmonic conjugate of u. This function is a harmonic conjugate of this function, because u plus iv is z square is a analytic function. Okay, but the reverse, if we say that u is a harmonic conjugate of v, in this case that this is a harmonic conjugate of v, that means we must write function of the form v plus iu, because imaginary part should be the harmonic conjugate of real part. But this function is not analytic anywhere. Okay, so if you check Cauchy-Riemann equations for this function, then you will find that the Cauchy-Riemann equations are satisfied only at origin and not at any other point z. Okay, so you can check that x derivative of this must be equal to y derivative of this. Okay, so that gives us y0, and y derivative of this must be minus of x derivative of this, that gives x0. Okay, so the function is not analytic anywhere. Okay, so it is, so if you have any function v which is harmonic conjugate of u, then this does not mean that we say that u is also a harmonic conjugate of v. Okay, no. Okay, so this was about harmonic functions. The definition of analytic function is now done. In the next lecture, we will learn how to construct an analytic function.